Jim Flynn, the Assistant Dean of Research Business Development here at the UMass Amherst College of Information and Computer Sciences. The next part of our symposium will include several research talks by our faculty and students. As the talks will show, we prioritize initiatives that will have a positive impact on the common good. If you have any questions during the talks, please feel free to post them via the question and answer feature that you can access through Zoom. We'll try to answer questions during or just after each talk. If we run out of time, you'll have a chance to join us in a breakout room, or we will follow up with you as soon as we can. Now, in our first presentation, UMass professor Beverly Woolf is going to discuss her research into artificial intelligence and the future of work. Here's Beverly.
Hi, this is Beverly Woolf. I'm a professor in the College of Information and Computer Science at the University of Massachusetts. I'm going to talk about AI and the future of work. This is actually a story about Jorge. Jorge is a regular, ordinary manufacturing worker, one of 13 million. However, Jorge is not trained for this workplace. There are 2.4 million jobs that will be unfilled in manufacturing alone due to the workers' lack of skills, which is a glaring skills gap. Number of openings and number of hires. And of course, coronavirus has exacerbated the situation. 20 million people receive unemployment. As the US economy reopens, a wave of job seeking never seen since World War II is going to take place. However, a person like Jorge doesn't know how to engage with robotics or electronic interfaces or smart workstations or connected factories. He or she has to learn new skills and knowledge not taught in schools today. We therefore first tried to understand the users. And we did this by interviewing 350 workers and employers, learned their skills and their beliefs and their preferences and their pain points, and identify how to incorporate pride and worker control into the jobs. And we worked with hundreds of workers and employers. Most were seeking jobs. The average age was 47. There were whites, Hispanics, and blacks, and it was mostly females. They said they preferred to be valued, to be treated equally, to have good safety practices over about 15 features that they were given. They know they should study active learning and critical thinking. And they know it's important to improve their digital skills and to train. And they would like training to be part of a career counseling. They also prefer the online training, and they prefer part-time to anything full-time or away from home. And an interesting one is they were asked whether they would like to take a higher wage job that is replaced by automation, or would they prefer a lower wage job that is not replaced by automation? And they preferred the lower wage job. So moving on, we saw that things that are needed is job matching. You have to take hundreds and thousands of job applications and match them with jobs given the specifications of the training a person has had, the experience a person has had, and see where the best match is, and the constraints, like won't work evenings or will work something else. So, and then continuous training that is on the site. They have to be able to handle the new machinery. And we have to do career path planning. What if they want a future job? What is required in terms of new training or experience? So I'm going to describe these two, actually just this one and that one, to help workers find jobs, personalize the training, and help them plan careers. So for continuous training and what Jorge needs, he needs immediate answers to questions. So if he's at a platform and there's an interface, what to do with the interface needs to be restarted if the robot makes some mistakes. What is the current training? Current training involves lectures. If you were to get training, it was and 6 months before or a year before, but it's probably not about the actual hardware and software that's in the factory. And some workers are not experienced even with technology, do not use laptops, nor computers, nor smartphones. So we have designed training that is consistent with Stanley Black & Decker robot. This is the robot, and previously a tool was put in a lathe and worked. However, that's a very dangerous and very dirty job. Now a robot does it and deposits the workpiece here. Well, what if the robot moves it in the wrong place? What if it starts having vibrations? What if it stops? What is this worker supposed to do? So we created a mobile interface where there's a menu of options for the operator so that he can be trained on what to do when this robot misbehaves, and what is the simulation of anonymous robot behavior. And so this system uses AI to track the behavior of the worker and the predicted behavior of the robot. What we're exploring is, can we use technology to be the teacher as opposed to another human? You can always bring another human over, but then you're taking that person away from their workstation. And this statement actually was made by a Stanley Black & Decker executive. So another system that we have designed is a stamping tutor, where it's an animation. This goes up and down, and this stamping tool will create a flat strip like this with a small hole and a slot here. And so the student is allowed to take out these pieces in order to figure out what new piece would be created by the stamping tutor. And these are all some of the features that can be used. And similarly, an injection molding tutor demonstrates how pellets are fed from a hopper to the barrel, and then you eject this kind of piece. And the student can play with different designs for doing this. So we're working on that, on AI-based training, and training materials focused on the worker's skill and behavior. And as the worker becomes more experienced, they begin to monitor the robot productivity and how can they ask questions of the robot situation, how can they get responses, and how can their answer contribute to the known incidents that might happen with this robot for that factory. The second system I'm going to talk about, the last one, career path planning. So this is a case where a person has a job, has 40,000, is earning 40,000 or maybe doesn't, but identifies the target job. This person wants to work with a CNC machine technician, wants to be a machine technician. CNC is a very expensive piece of equipment that takes a lot of training and can break down easily. And this job would be 90,000 as opposed, so it would be a change of 320K over total earnings. So what would be needed? We use, again, hundreds of thousands of listings of people's jobs and of training that's required and of experience that's required to match this person. And what we see is that first they might need just the CNC operation certificate, which you can get part-time, and we show them where. And what's the intermediate job might be a machine operator. It goes up now to 50,000 a year. And then maybe he needs an engineering degree from community college. So each of these responses planning is done individually for a person based on their training and based on looking at hundreds of thousands of other jobs and other people's activities. So we've got continuous training, career path planning, and job matching, which I did not describe to you, but it involves, again, looking at this person's resume and matching it with jobs nearby or constraints that this person has. So we're working with Jorge and moving forward together and getting him trained for the new workplace. Thank you.
Thanks, Beverly, for a great talk. Is Beverly able to turn on your video to come on and answer a quick question? We have a little bit of time in between talks.
Yes, I'm here, and I will turn on my video if someone will let me.
Okay. Well, we could hear you, so at least we have that.
Okay, I'm here.
Hi, Beverly. Thanks for a great talk. One of the questions that came in through the chat is that this research effort was conducted in conjunction with one of our college's industry partners, Stanley Black & Decker. Have they taken the results of this and put it into practice, or is there a direction of how they're going to use this, either from business practice or a policy change going forward?
So we have not implemented this in the factory because we had a lockdown for the last year. However, the plans are to bring us into the factory to actually choose a robot or a workstation to develop this on. And then the implication is that certainly we're working with the Chief Technology Officer. This is Mark Maybury, and he has stated that in manufacturing 4.0, this is part of the policy. So there should be a move to not only train these people, but receive their questions, receive their inquiries, and build up a community reservoir of knowledge so that we have solutions to these events. And after a year or so, all the solutions would be put in from other people, and the person at the workstation would just ask a question and the answer would be found. Or if you were in a worker and you supplied a new answer, perhaps it would be acknowledged throughout the factory or throughout the company that you have a solution. So there have been a lot of discussions about how to integrate it into the company, yes. There's another question I see. How does Jorge afford $50K over a 2-year period to get the necessary degree? Yeah, this is the big problem. We worry that such workers, and we're talking about people with a high school diploma, but maybe nothing more, and with family responsibilities, where can they go and what can they do if they have to be at the factory all the time? So we certainly discourage a lot of like leaving for 6 months or leaving for 2 years to get training. And we're figuring that the kind of implements that we're developing on site should be more effective and should not, should be free actually from the manufacturer. And that's another point, that manufacturers are going to take much more responsibility for this kind of training. They're recognizing that it would be better to keep an employed person on as opposed to taking a new person who might have these skills. It'd be better to train the incumbent worker.
Great. Thank you so much, Beverly, for being here. We're now, because of time constraints, we're going to move on to our next faculty research talk. Professor Deepak Ganesan. He will discuss the opportunities and challenges related to research into deploying health sensors in normal everyday clothing. Over to you, Deepak.
Hello, everyone. My name is Deepak Ganesan, and I'm a professor of computer science at UMass Amherst. And today I'll be talking about some of our recent work on rethinking wearable devices, and rather than using traditional wearables, thinking about everyday clothing as the substrate for sensing various aspects of human health. So when we think about wearable devices, we tend to think about the Fitbits and the Apple Watches and all of these devices we find in the market. All of them are electronics based, so you can have these earbuds with sensors in them, eyeglasses with sensors, rings that can measure sleep, ECG monitoring patches, and of course athletic garments with sensors embedded in them. But a few years back, I got into a discussion with one of my colleagues in chemistry, Trisha Andrew, and she works in this area of functionalizing textiles and functionalizing fabric to act as sensors. So taking cotton threads and silk threads and so on and functionalizing them so that they can actually sense various things. You can also do things like energy harvesting with the same threads. And so this got us, really excited, and we started imagining a new way of thinking about wearable sensing. So rather than thinking about discrete wearable sensors like the ones we have today, we wanted to rethink everyday clothing. So so what I show here is sleepwear. We wanted to reimagine sleepwear. How can we turn pajamas into a substrate for sensing things about sleep? And sleep is a very important area in the area of health sensing, because there's a lot of implications. Sleep disorders are a big problem. It's hard to monitor sleep in an unobtrusive and easy manner. It's really hard to monitor, for example, the brain signals. And there's a lot of useful information and research being done in the context of sleep. So we wanted to monitor various aspects of sleep. And the key difference here being that rather than thinking about traditional electronics, we wanted the thread itself to be the sensor. The whole substrate of these pajamas is essentially a thread-based sensor or fabric-based sensing substrate without discrete electronics in the garment. The only discrete electronics would be the buttons, where there would be a processor and a radio and so on. But the rest of it would just be the standard silk and cotton garments. So the challenge, though, is how do we sense using loose-fitting clothing? I mean, the rule of thumb in wearables is that you need a reasonably tight fit in order to get a good signal. And that is the reason why in all of the cases you see on the left, people have embedded sensors, these discrete sensors in sort of relatively snug fitting devices, right? The ring is snug fitting, the watch is reasonably snug fitting, the earbud is tight fitting, and so on. But we want to do this with loose fitting garments, and that is quite a challenge. And the biggest challenge perhaps with loose fitting garments is that you're not guaranteed that there will be a very strong contact with any particular part of the body. So the idea here was that we, even though the garment itself is loose fitting, there's many opportunities where we have enough pressure and we have, we can rethink how we sense in many different ways. The first way we can think about sensing with loose fitting garments is that even though these textiles are loose fitting, we do have pressure between the textile and various surfaces against which we press, right? So if you're sitting on a chair, then your back is pressed against a chair and there's enough of contact. If you're lying down, then there's pressure between the body and the bed, as well as, if the blanket is pressing down on you, then also there's a pressure created by that. So there's pressure in various ways. Now, even when you're not pressed against a particular substrate, parts of the body are pressed against each other. For example, if my hand is resting against my torso, the hand is putting pressure on the torso, and that creates enough of a contact that you can, and not necessarily direct contact, but enough pressure so that you can actually get, extract some of these signals from the body. Now, what happens if neither of these are true? What happens if you're not pressed against a surface and really you don't have much pressure between different limbs? Even then, interestingly, you can rethink how the fabric actually behaves. Loose-fitting fabrics, crumple and move a lot, right? For example, as you're breathing, fabrics move with your breathing. As you breathe in and out, your fabric moves with you. Similarly, as you extend or flex your arm, and as you extend or flex your knee, your fabric is, your textile is, compressing and expanding. It's sort of crumpling with these movements. And so, you have to reimagine what these crumpling and these kind of changes in the structure of the textile can be leveraged as a way of sensing. And so that's the other thing that we can leverage, that the textile itself is a flexible substrate, and the foldings are potentially things that we can sense. So this raises a whole lot of challenges that we address in our research. And I've listed them here. So the loose fitting, for example, is a double-edged sword. On one hand, you have all of these dynamics, the folding and the crumpling and so on, which you can measure. On the other hand, you have a lot of motion artifacts, which can affect the signal. Similarly, large surface area is a double-edged sword as well. Large, compared to other traditional wearables, which is in like one place in the body, like for example, the wrist. The textile covers a large fraction of the body, and so you have a huge sensing area to work with, but also a lot of noise because everything is moving together. There's a lot of variability as well because people are different, their body weights are different, the pressure they apply is different, and so we have to be able to deal with all of these huge dynamic range in pressure and the types of movements and the types of things people do. The opportunistic sensing also means that no one location in the body on the textile is guaranteed to give you a great signal. So you really have to sort of sense everywhere and collectively look at the data from lots of different places on the textile as opposed to one location in the textile. And finally, we're talking about very weak signals, right? I mean, extracting a small signal from the body is non-trivial. And one of the things we quickly realized is that existing textile-based sensors would not work in many cases, would not work in the types of scenarios and the types of signals that we were looking at. So a lot of this work was essentially a very ground-up effort. We had to redesign the sensor. So from the ground up, there were new functionalization techniques, new sensing techniques, and new ways of analyzing the data and dealing with noise, and then all the way up to the application. So let me show you a couple of quick examples of some of the things we've designed. So the pajama, we call it the pyjamas, sort of physiological sensing pajamas. And so this can measure heartbeats and respiration and joint movement. So again, it's a distributed sensing substrate. in the sense that there's lots of different sensor patches and different types of sensors, because the types of dynamics in different parts of the body are different. So in the figure here, there's 4 pressure-based sensors, both in the back and the front, to take advantage of instances where there's pressure between the torso and some external surface. There's also a triboelectric sensor which can deal with which can work under very dynamic conditions. So I mentioned, as the textile moves with the individual as they breathe in and out, and these tribo sensors can measure those kinds of dynamic signals. And then on the various limbs, on the various joints, we have an additional triboelectric sensor that can measure the folding and the crumpling and the expansion as you fold and expand. You fold and your joints. So let's take a look at cardiovascular rhythm and see how you can measure that. Cardiorespiratory rhythm. So the idea here is that when there's pressure, we can measure the ballistics of the heart. So whenever the heart pumps, there's a ballistic action, and there is there's a very small, very tiny amount of ballistic pressure exerted, but that's potentially enough. So we developed a very sensitive resistive pressure sensor, textile-based resistive sensor that can actually measure these tiny changes caused by these ballistics. But you can get a lot of very interesting signals from the pressure. So the baseline gives you things like posture, which side you tossing and turning when you're sleeping. The envelope gives you the respiration signal. As you breathe in and out, the envelope changes for this pressure signal. And then finally, these tiny ripples are caused by the ballistic signals of the heart, and you can measure the heart-related signals from the ballistics. And then, of course, you need a computational pipeline, because you're fusing data from lots of patches, right? You have these sensor patches in different locations. You don't know which one is giving the best signal, and multiple of them may be giving a good signal at any given time. So you're taking all of these signals, you're extracting features from these different patches, and then you're determining, you're classifying it, or you're reconstructing what the heart signal looks like. So you have to look at the signal quality across the different patches. You have to do sensor fusion, and also you have to deal with timing mismatches, because the signal is not observed at the same time in all of these different patches. And of course, and finally, all of this depends on the individual. So all of this, different individuals can work extremely differently. The signals can look very different across different individuals. So no single model will work, well across everyone. So, we've shown that this can work really well across 20 subjects, men, women, and across different sizes, different body mass indexes, and so on. Now, this is just a very quick video, and so what this shows here is 4 patches signal on the top there, the voltage changing, and you can see as this person turns, their posture changes, so we detect the posture. And the signals also, you can clearly see the breathing waveform. You can also clearly see that the tossing and turning causes these 4 patches to observe different signals, which is what we leverage to do our detection. We've measured a number of other things. I'll briefly mention those as well. So for example, the triboelectric sensor on the joints can measure these expansion and compression of these textiles, the crumpling that I talked about. And so from that, we've shown that you can measure all kinds of activities, just the daily activities that people do. In fact, we can also sort of see things like perspiration and sweating. The textile sensors are also sensitive to those, so we can also get a glimpse at that information, which is valuable. We have also shown designed a sleep mask, which can get at some of the most important signals in sleep, which is the EEG signal, the electrical signals from the brain. And we've designed the signal processing, the hardware, the signal processing, the data processing stages. And so what we've shown is, and this shows you a quick video of not the sleep part, but as my student is moving her eyes, you can clearly see the signal coming in from these textile-based sensors in the mask that she's wearing. So what we've shown is that the sleep parameters we obtain after all of the processing, the sleep parameters that we obtain from our phi mask, which is what we call the device, is much closer to the ground truth polysomnography, which has a whole bunch of electrodes. This is a thing you would do in a sleep clinic, but it's a lot better than what you get from a Fitbit or an Oura Ring or one of these devices in the market. So all of our work has been published in very interdisciplinary forums, both on the computing side and on the material side. And I wanted to thank the team which has worked on this, my chemistry collaborator, Trisha, ECE collaborator, Jeremy, and all of our students.
Thank you, Deepak, for that talk. Deepak, are you out there and can you turn on your video right now? Hi, Deepak.
Yep. Hello.
Yeah, thank you so much. We have just a couple of minutes for a quick question. One that came in over the Q&A, and that's about that sensors typically require electricity. And when these sensors are built into clothing, what happens when they come into contact with water? Is that a challenge that you've looked at?
Yeah, they have a hydrophobic coating on them. So they're actually, in fact, many of these sensors, they've gone through many wash cycles in a washing machine to make sure that they work across, I think, 20 wash cycles or so. And yeah, I mean, I think, as with every sensor, they're very low power, but essentially we have conductive threads that go to the different places in the garments, and there's a button that connects to those. So all the sensors are connected to these button-sized, I mean, I think we didn't show that in the video. I didn't show that in the video, but yeah, you have these button-sized electronics boards, which have a battery on them, and that's powering the different sensors. The different sensors are connected through conductive threads. So everything on the textile is threads except these buttons.
Okay, great. Before we move on to our next talk, I just want to ask, can I get my pajamas in pinstripe and flannel?
My student is working on, trying to take these and commercialize it, but we'll see how that goes.
Great. Thank you so much, Deepak. Okay, in our next talk, Assistant Professor Ina Fiterau will discuss projects at her Information Fusion Lab involving heterogeneous multimodal data. We'll also hear from two of our PhD students who will discuss their promising research into predicting heart anomalies and early forecasting of Alzheimer's disease. Here's Ina.
Welcome to the CICS Symposium. I am Ina Fiterau, an assistant professor at CICS, here to give an overview of the Information Fusion Lab. The Information Fusion Lab is focused on machine learning for multimodal data, including methods that support a wide range of biomedical applications. Over the last 2 decades, we've seen a sharp increase in data abundance, opening new possibilities for the training of machine learning models, both in terms of variety and scale. In the area of health, specifically, electronic health records are widely collected and increasingly made public. Smartphones and wearables have become ubiquitous, leading to a democratization of data collection. This has led to a surge in multimodal data that's noisy and non-uniform. These datasets are collected across multiple populations and institutions at an unprecedented scale. Over the years, we've seen powerful specialized techniques that have been designed to handle distinct data types such as images, time series, and videos. However, comparatively less effort has been allocated to approaches that can address multimodal heterogeneous data collected in a non-uniform manner across multiple sources, despite its prevalence in real-world settings and its potential to improve prediction over single-source models. We'd like to find ways to integrate these many different types of data, as well as make them more accessible to users. All in all, the aim of our lab is to build hybrid systems that integrate multimodal, multi-source data and learn models that aid users interpret this data. Our research includes a wide variety of topics. Deep learning for the fusion of multi-resolution time series, images, and structured information. The incorporation of domain knowledge, or saliency in images, and the integration of multiple views for MRI analysis. Most recently, we introduced new models for normalizing flows and transfer of causal models. We apply our methodology to enable the early forecasting of Alzheimer's disease, the detection of heart anomalies, and the prevention of accidents in self-driving cars. In so doing, we are advancing the objective of CICS to use data science for the common good. We have a diverse team of award-winning PhD students. In the next part of the video, they will present some of the research they have been doing in the lab. Thank you for your continued attention.
Hi, I'm Ke Xiao, second-year PhD student in the Information Fusion Lab. My research area is machine learning on medical imaging, mainly with cardiac MRI datasets, including weak supervision, computer vision, and segmentation. I worked on various computer vision projects using cardiac MRI datasets. Yin and I started working on the detection of bicuspid aortic valve disease at Stanford, and have continued this work now that I have started my PhD at UMass. Most recently, we have been working on the detection of mitral regurgitation and several image segmentation problems. Normal aortic valve has 3 cuspids, and due to congenital condition and unhealthy lifestyles, it could lead to a malformation of bicuspid valve. And if left undetected and untreated, it could lead to cardiac arrest or worse. The main difficulty in this project is that the condition has a prevalence of less than 2% in general population and only about 6% in our dataset. On top of this, we are working with unlabeled datasets from the UK Biobank. Here are some examples of tricuspid aortic valve and bicuspid aortic valve MR data. And this is the model pipeline where we applied domain knowledge on processed segments to form noisy, weak labels, which is in turn used to train a deep neural network model to generate the final predictions. In the final classification results, we have a 61% improvement in F1 score and a 171% improvement in precision. And model improves even further as we add more unlabeled data. In the t-SNE plot, we can see a clear separation, and even those misclassified cases look very similar to the BAV cases due to reasons like image quality and mild conditions. In the survival analysis we conducted, our predictions are corroborated with the findings. Our next project is the mitral valve regurgitation project. The mitral valve is the valve connecting the left atrium and the left ventricle of the heart. Mitral valve regurgitation is the condition where the blood flows back from the left ventricle into the left atrium. And if left undetected and untreated, it will lead to severe complications, including pulmonary edema, blood clots, stroke, heart failure. Here are some examples of the positive and negative mitral regurgitation cases in the 4-chamber view and 2-chamber view of the MRI data. And this is the model pipeline where we apply the masks generated from a segmentation model to the MRI, which is then used to train a deep neural network model. This is the pulmonary artery and aorta segmentation model I worked on. Segmentation is a useful method often employed to focus on the part of the image which is useful of the task at hand. In this project, I used methods like Hoff transform, watershed segmentation to segment the ascending, descending aorta, and the pulmonary artery. And finally, this is the 4-chamber view segmentation I worked on. Thanks.
Hi, I'm Sidong Zhang, a first-year PhD student in the InfoFusion Lab, and I will talk about Project Forethought. The objective of Project Forethought is the detection of Alzheimer's disease at least 2 years before symptom onset. To achieve this goal, we are applying deep learning models to multimodal patient data including brain magnetic resonance images. Alzheimer's disease is a condition that causes brain degeneration and, as a consequence, cognitive decline. Alzheimer's is irreversible. So far, every clinical trial for a cure has failed. The best chance of combating Alzheimer's is to detect early pathological changes in the brain prior to the onset of mild cognitive impairment. This makes it possible to conduct clinical trials on pre-Alzheimer's cohorts and paving the way to preventative treatment. We train forecasting models on the full multi-model dataset provided by the Alzheimer's Disease Neuroimaging Initiative. The study includes subjects that show signs of cognitive impairment and Alzheimer's, as well as healthy controls. Multimodal data, including brain MRI scans, cognitive test scores, and biomarkers, are collected from subjects over multiple visits, spaced 3 to 6 months apart. We believe deep learning models can identify potential pathological changes in the multimodal data, thereby forecasting Alzheimer's onset. The video shows an example of brain MRI representing different cross-sections of the brain, scanned from top to bottom. Here we show how the degenerative process affects one slice of the brain. The subject transits from cognitive normal to mild cognitive impairment to Alzheimer's disease over the course of the study. We expect the model can learn from the multimodal trajectory of patients and generate informative features that indicate the patient's status in 2 years' time. Our current model is called FLAIR. The trajectory data are first encoded to feature space F, representing the subject's health state. Then we use time series models to forecast the future health state F hat, and from the health state F hat, we obtain the future disease label Y hat. The model is trained by minimizing the trajectory prediction loss and disease forecasting loss. The trajectory prediction loss is a difference between the predicted next health state in the trajectory F sub VI hat and the actual next health state F sub VI. The forecasting loss is a common cross-entropy loss on the predicted label Y hat and the actual disease label Y, tau visits in the future. Our current results shows that the model working on demographic information and cognitive test scores together can reach an average score of 0.82 in the 18-month forecasting task, which is a considerable improvement over the baseline. That brings us closer to our goal of detecting Alzheimer's at least 2 years before symptom onset, opening the door for clinical trials of preventative drugs. Thanks.
Thank you for listening to that presentation on the medical imaging projects ongoing within the Information Fusion Lab. Our full video in the Symposium showcase contains overviews of 2 more projects. One project is on applying deep saliency to pedestrian detection. The other is a more theoretical project on changing dimensions in normalizing flows. Do check out some of our other projects, which include handling multi-resolution time series and incorporating clinical nodes. Their descriptions are up on our lab website. Please.
Okay, thank you, Ina, and thank you to your wonderful PhD students for a great presentation. We're on a sort of a tight time schedule, so I just want to ask you one quick question that came in through the chat. As I watch this, and I think I've mentioned to you before, this is incredibly promising research and could help a lot of people. What do you see as the major impediments for getting these models applied in the real world Do you see your lab or your students working on any of those challenges?
Okay, thank you. Thank you for the compliment, and that's an excellent question. I would say that there's a barrier between getting these. So let's take the Alzheimer's project, right? We have a classifier that tells us that, hey, 2 years down the line, a person might get Alzheimer's disease. So what we want to do is actually have a pipeline, whereas in contingent of people that are at risk come in, and we put them through this classifier, and we select the people that are at risk, and then direct them towards palliative care or clinical trials or something like that. To get there, we actually need confidence that our model predicts well, and it doesn't actually. It has a pretty high precision, a pretty high recall, and that it's not going to put people through clinical trials that don't necessarily need that drug. So it's a question of evaluating the robustness of a model. And when you're talking about data from, a few hundred or maybe even a few thousand patients, sometimes it's challenging to get that level of significance and confidence. We are currently working on that. So if we could bolster that by using unlabeled data from, say, the UK Biobank or another data set, that would be helpful. And we are working towards these challenges. So securing more data sources, a larger contingent of the population, and perhaps testing our Alzheimer's predictive model in the same way in which we evaluated our cardiac anomaly detection model and looked at downstream data.
Great. I actually suspect that there may be some people in attendance, some industry partners that may be able to help with that data challenge. But thank you so much.
For sure. Thank you. Thank you so much.
Thank you for the talk. Next, we're going to move on to Dr. Mohammad Hajiesmaili, who is a member of our research faculty here at the College of Information and Computer Sciences. He's going to discuss his research into carbon intelligent distributed systems. Over to you, Mohammad.
Hello, everyone. My name is Mohammad Hajiesmaili, and I am a research faculty with the College of Information and Computer Sciences at UMass Amherst. I'm going to talk about a quick overview of our research at UMass. And so the topic of my talk is on carbon intelligent distributed systems, where we are using a robust and data-driven approach to tackle those problems. So let me begin with a quick motivation. So perhaps most of you have seen this recent nice plot that talks about the compute infrastructure needed for doing state-of-the-art AI models. And the nice observation here is that the compute infrastructure like CPU and memory needed for doing state-of-the-art AI models has been doubled every 3.4 months from 2012 to 2018, which shows a huge exponential increase of around 300,000 from 2012 to 2018. Just to imagine how big is this number, you can see that with the same interval, Moore's law implies an increase of just 7 times as compared to this 300,000th time. So this has apparently a lot of consequences in affordability and a lot of issues, but one of the most important and foundational consequences is the energy usage of this compute infrastructure needed to run those AI models. That could be translated into huge increase in the carbon footprint of AI models. So that's one example. The other example is this recent popularity of Bitcoin that has, again, some sort of consequences in the foundational energy requirement to mine Bitcoins. And so recent articles shows that, for example, this article shows that Bitcoin currently is consuming more electricity than the entire Argentina. And this number is going to increase again at some sort of exponential growth. And there are some articles recently published, like in Nature, that forecast the total energy demand of ICT domain by 2030. And it shows that, okay, so the expected energy demand of the entire ICT sector will be around 21% of the entire electricity needed for the entire planet, and on average case. And even with the best kind of prediction, ICT energy demand grows to around 8% of total energy demand of the entire world, which is still a substantial amount of energy. And so towards kind of tackling these issues, there are definitely a lot of effort on developing research and at the intersection of sustainability and AI at a lot of different levels. Like, for example, in the core AI models, there are a lot of efforts to develop some sort of green AI or green ML models that you can see a few examples here, like for green AI, or there is a recent article in our actually college that shows that, okay, so training a single AI model can emit as much carbon as 5 cars in their lifetime. And so deep learning has a terrible carbon footprint. So this is some sort of like efforts in for the developing core sustainable AI models, but you can see a lot of additional efforts in the entire spectrum of digital infrastructure to make the entire ecosystem to be more sustainable, like some efforts talking about energy efficient device placement of neural networks, or energy efficient scheduling of AI workload, or like something on the facility level, that, for example, a recent article by DeepMind is proposing some sort of deep learning models to reduce the cooling bill of data centers by around 40%. And so these are all efforts. And what we do actually is kind of in the last mile of this ecosystem, where our goal is to develop some foundational theories and machine learning tools for carbon intelligent data centers. That this research actually is supported by a Google Faculty Research Award and a recent NSF Career Award in 2021. And so the motivation here is that, okay, so a lot of companies, they follow this ambitious goal that they say, okay, so the internet is a 24/7 service, and it could be, or it should be, a 24 carbon-free service as well. And so towards this ambitious goal in 2020, a lot of these companies like Microsoft claim to be carbon negative by 2030. Apple commits to be 100% carbon neutral in 2030. Actually, Google announced that right now, even these days, their data centers are working harder when the renewable is plentiful. And here you can see the Amazon's commitment to be carbon zero by 2040. And so there are a lot of efforts in this domain. And so right now, I'd like to just dive into one technical topic that actually is something that we are doing here, and show how these are nice, interesting research problems, and how we are developing some sort of AI and machine learning models to develop these sort of problems. Okay, so the problem that we are going to talk about is supported by a Google award and NSF grants. So the topic is on data center energy optimization, and the very, very basic scenario that we are going to talk about is like this, that you do have some energy load from data center that it could be divided into elastic and inelastic loads. That by elastic, I mean, it could be kind of is kind of time shiftable over time, but inelastic, some sort of immediate load that should be executed immediately. But anyway, this load could be satisfied from a portfolio of energy sources, like from the electric grid, from the local on-site renewable sources, or from large-scale on-site renewable, on-site energy storage systems. And the question is that, okay, so what is the right energy flow among these different sources such that by the end of the day, you can satisfy the energy demand of your facility and at the same time maximize the usage of clean energy or green energy and minimize the cost of using energy from electric grid. Okay, so that's the question that we are trying to answer here. And why this question is a challenging question here, you can see that the challenge really is coming from the uncertainty, and everything almost in this scenario is kind of uncertain because, okay, so you can see the energy demand of the data center is changing over time, and once it's included or integrated with the renewable sources like wind, it becomes even more unpredictable. That's one part that is an uncertainty in the problem. The other domain of uncertainty is about the price of energy, which is again kind of unpredictable because it follows some sort of energy market rules. And so in this problem, we are kind of dealing with a scenario that is really a multidimensional uncertainty and how we tackle this problem. So we kind of have two approach. One of them is a little bit more theoretical approach that we just write down this as an optimization problem, but this optimization problem looks very simple and straightforward. But what makes this problem to be challenging is that really we don't know the input to this optimization problem. And we are going to develop some sort of foundational theories to show that, okay, so if we don't know what's going to happen in the future in this sort of online decision-making scenario or online optimization scenario, how we can make sure that the algorithms that we are developing are um, provably efficient against those uncertainties. And so we developed some sort of nice theoretical algorithms with nice bounds and theories behind them. And we have shown that, okay, so our algorithms are best that you can do without knowing anything in the future. However, this like preliminary sort of experimental results shows that, okay, so even though these are the best possible things in theory, but since we don't know, we don't have any assumption about the uncertainty of the model, they still are not so good. There is a gap between what the algorithm does and what is the best possible optimal solution. And so what we are proposing here is just to fill this gap with developing some sort of nice state-of-the-art ML frameworks to further improve these algorithms using data-driven approaches. Okay, so that was like a quick overview of one of our projects in this domain. We do have a lot of other projects in this domain at the intersection of both foundational theoretical problems and also some nice kind of application domain scenarios. And most of them are kind of involved in both theory and applications. And if you are interested more on our projects, feel free to visit our homepage at UMass. And so there are a lot of other projects there that are almost all of them are in this like domain of sustainability and AI. And so let me just wrap up and conclude my talk by a quote by Bill Gates in his letter to the class of 2017, that somewhere in the middle he says that, okay, so if I were starting out today looking for the same kind of opportunity to make a big impact in the world, I would consider three fields. One of them is artificial intelligence. The second is energy, because making it clean, affordable, and reliable will be essential for fighting poverty and climate change. And the third one is bioscience. So what we are doing is a research at the intersection of AI and energy. And thank you for your listening.
Thank you, Mohammed. Great talk. If you, we have a couple of minutes, so just a quick question that came in through the chat. What do you see as driving a lot of the improvements going forward in terms of efficiency? Do you see the AI algorithms themselves getting better, or do you see the hardware that is running them as providing the innovation to be more efficient?
Can you hear me?
Yes.
Good, good. Thank you, first of all. And that's a great question. So as somewhere in the middle of my talk, I mentioned, in the entire, I would say, life cycle of this computing domain, there are a lot of activities to make the entire system to be more efficient. Um, for example, there are a lot of effort right now just to make the core AI models to be more energy efficient or efficient at large. And also in terms of like hardware design, there are a lot of effort still ongoing on. But the point is that for example, for hardware, um, uh, there is a a little bit of room for further improvement. And what people are trying these days is just to, okay, so one of them is just to make the training side or the software side to be more efficient in terms of energy usage. But there is still a cap over there also. And the main effort is just to kind of make the entire system to be aware of the carbon emission. And so we cannot improve the energy anymore, perhaps, but we can definitely improve the carbon emission, but by just be intelligent on when and where we are running those sort of workload. And that's something that actually is getting a lot of attention these days. And me personally, I'm getting very interested in making things to be more carbon efficient as compared to the traditional approach of being energy efficient.
Thank you, Mohammed, for answering that question.
Sure.
We're going to move on to our next two talks today. The next up, we're going to hear from Prashant Shenoy, who is a distinguished professor and associate dean here at the College of Information and Computer Sciences. He's going to talk about the data-driven approach he has taken to creating sustainable smart cities. Take it away, Prashant.
Hello, my name is Prashanth Sethi, and I'm a professor in the College of Information and Computer Science at the University of Massachusetts. In this talk, I'm going to describe some of our ongoing research on smart cities and specifically sustainable smart cities. So let me start with some motivation for our research. As we all know, the Internet of Things have now become commonplace, and there are sensors and actuators that you can now embed everywhere in the physical environment at low cost. There are already more than 25 billion such devices that have been deployed in recent years, and that number is expected to grow dramatically in the coming years. This has been a result of the miniaturization of technology and the ability to embed ubiquitous wireless connectivity into devices and into sensors in the physical infrastructure. The rise of IoT has led to the emergence of several new application domains that are broadly related to smart and connected cities. These range from smart health as a result of availability of wearable devices, smart buildings and smart homes, smart transportation, precision agriculture, smart manufacturing, and so on. Now, our work views these domains as data-driven cyber-physical systems. Now, cyber-physical systems are systems that link the physical world to the cyber world. And this is done through the integration of computing and networking that allows us to monitor, analyze and control physical processes. Now, an example of such a cyber physical system is the heating and cooling system that you might have in a home or a building, which is often controlled by a smart thermostat. In this case, it's Google's Nest thermostat that can be controlled to the cloud. That also controls your physical infrastructure, which is the air conditioner or the heating system. Now, both this cyber and physical systems also are coupled with humans that live in the environment and are impacted by the heating and cooling system through comfort that it provides. Now, our work specifically looks at data-driven systems, which can be characterized by sense, analyze, and response systems that are shown in this figure on the right here, where you take data from sensors, you analyze it through various means, including, as we will see, machine learning techniques, and then you can provide feedback to users or actuate your sensors. And cyber physical systems are increasingly using this data-driven sense, analyze, respond architecture. And there are two examples shown in this figure. One is from smart transportation or fleet management, where there are sensors that are deployed onto vehicles that have cellular connectivity. They send their sensor data to the clouds, where it's subjected to analytics. And then you can give feedback to drivers saying it's time to take a break. You may be getting tired from a long drive, or more intelligent optimization such as scheduling services and so on. The other example here is a smart electric grid, where you have flexible loads or meters that actually can monitor the electricity usage of these loads, that communicate with a smart electric grid and have ability to control these loads through techniques that are referred to as demand response and so on. Now, our research looks at these problems of data-driven cyber-physical system through different lenses. The first one is looking at it from a systems perspective, and the other is looking at it from the AI perspective. And in reality, you have to actually look at it from both perspectives. So what you need is a symbiotic approach that addresses these problems both from a systems and from an AI perspective. Now, what I'll do now is describe some of our ongoing research efforts that look at data-driven cyber-physical systems from both an AI and a systems perspective. And in particular, I'm going to focus on the energy domain and talk about sustainable smart communities. Now, here we have communities, there could be cities or they could be villages that want to live sustainably. And by that, we mean that they need to consume natural resources such as energy, water, food in a sustainable manner. Now, one way to do this is to make the community net zero or even zero carbon, which means that the amount of energy or carbon it consumes is neutral in some fashion. And there are many technological innovations that have emerged in recent years that are going to allow us to design net zero energy communities in the future. And these range from renewable energy such as solar and wind, and energy storage such as batteries, electric vehicles, as well as buildings that are themselves intelligent and net zero in some fashion. So I'm going to now describe some work that we have been undertaking in our research lab that addresses some of these issues. So I'll describe 4 specific projects, which are nuggets that provide some glimpse into how we are approaching these problems, both from an AI perspective, as well as we will see, from a systems perspective. So the first project is called Solar Click, that is shown on the left on this slide. And what Solar Click is designed for is a problem called anomaly detection. So here we have solar arrays that have been deployed. They may be there on rooftops of homes or buildings, and often they might have developed some sort of electric fault, or the array may be covered with dust or snow, and it may be producing less than its optimal capability. Now we want to detect when such problems occur and alert either the homeowner or the operator saying there is a problem, you need to come and fix it. So what we have done is we have developed a technique that we refer to as sensorless anomaly detection. Whereas the traditional approach for trying to figure out if there is a fault is to actually deploy sensors on these arrays, which can monitor the production. And if you see a production loss, you can send an alert. But often these arrays don't have any sensors deployed on them. So our technique actually does not require any sensors. Rather, it uses a machine learning technique that looks at a peer group of arrays, which are solar arrays that may be nearby in that community or in that city, and it uses the production data from those peer groups to predict what could be the production of the solar array. And the idea here is the weather in a region is going to be similar. It may be sunny or it may be cloudy, and the entire region might see that a similar weather pattern. So solar arrays that are deployed maybe in a neighborhood or in a small town or in a region will have similar generation. And we exploit these correlations to design a model that allows us to predict the generation of this array. And if the observed generation deviates from the predicted generation, you know that there is a problem. And we can deal with issues such as transient factors, such as shadows from nearby trees and so on. And we have shown that this kind of technique scales to a very large number of solar sites globally without requiring any new instrumentation. Now, the second project that I want to describe is called Deep Roof. Now, this technique uses computer vision to decide which rooftops of buildings or homes are good candidate for deploying solar arrays. And this is shown in the picture here, where you take a Google Map satellite view of a particular address that shows you the aerial view of that location. And then in that view, we can detect what is actually a building, what are nearby trees, and so on. And you do this using computer vision techniques. And then once you have determined which is the roof, we can actually do further analysis to extract the roof structure, the planes of the roof, what direction they face, and so on. And then you analyze that structure to figure out what planes are actually good candidates. So at the picture on the right, you see that there's one plane that is labeled green and one red that says that the south facing plane, which is green, is going to get maximum sunlight despite the presence of a tree nearby. You will still have highest production, and that would be a good candidate for installing solar arrays. Now, for a long time, this type of analysis has been done manually by having someone actually look at the site or at least look at the images. What we have done is automated this and built a system that allows us to do this for an entire city and all the buildings in the city. So you can quickly identify all the buildings and rooftops that are good candidates for solar installations. Now, the next project I want to talk about is called What Home. Now here we are using machine learning techniques together with systems approaches to decide which buildings or homes are inefficient in terms of their energy usage. So the interesting thing here is we combine a physics model that are used by energy experts to model the energy usage of a building with machine learning techniques that allow us to deal with the stochastic nature of the energy usage. And the idea here is, an older the building, the worse maybe its envelope or windows, and the higher its energy consumption. So what we do is we normalize the energy usage of homes by age, by size, and then use our machine learning technique to model the energy usage and its dependence on temperature. The more sensitive the energy usage to temperature, the less inefficient the building is going to be. And we find outliers in peer groups of buildings that are categorized by, say, age and size. And the idea is to find anomalies or anomalous usage patterns that tell us that something is wrong. And although it's not shown here in this slide, our machine learning techniques are also capable of classifying the types of problems that you might see, saying that maybe the air conditioner in the house is old, or the windows are old and they're leaking thermal energy and need to be replaced. or that the thermostat is misprogrammed and needs to be fixed. So we can not only find what kinds of anomalies exist, we can also find the cause of this anomalous behavior. Again, this type of technique is being designed in the context of city scale energy analysis, where we can analyze all the structures or buildings in a city, its energy usage, and find the worst offenders. The last project that I want to describe here is called vSolar. And here, what we are doing is using techniques that are well known in operating systems, networking, and distributed systems, and applying it in the energy context. So what we have done, as is shown in the figure on the right, is to build an energy virtualization layer where you can take physical assets such as solar array and expose virtual solar arrays that you can then assign to a homeowner or maybe a owner within an apartment building where all the owners share a common physical array. So each homeowner gets an abstraction of a virtual array and a virtual battery that they own that they can use in any way they want, rather than depending on how the community as a whole uses the physical assets. So it exposes, in other words, independent control and multiplexes virtual resources onto physical resources, similar to how OS virtualization allows us to multiplex virtual computing resources onto physical resources. Now, interestingly, this kind of technique can be used to implement energy trading between owners, as well as allow you independent control of your share of a physical solar array's electric generation, or your share of how much energy is stored in a battery. So these 4 projects give a glimpse of our research that spans both AI techniques as well as systems techniques, and address interesting sustainability problems and allow us to design techniques that will put us on a path for a net zero future. So with that, I'm going to end the presentation, and I would like to point to 2 websites where you can find more information about our research as well as access to research papers. Thank you very much.
Okay, wonderful presentation. Unfortunately, due to a scheduling conflict, Prashant is unable to be here for the short question and answer period that we have between videos. So we get a little bit of time back, and probably I'll just take this opportunity to let you know that all of our featured talks, plus a large number of other research talks that our PhD students and other faculty members have done, are accessible online, and we'll be releasing the featured talks tonight and tomorrow. But if you go to symposium.cics.umass.edu, you can see a lot of those talks. So moving on to our next talk, Guan, who is an assistant professor at the College of Information and Computer Sciences, will give a talk entitled Recurrent Neural Networks Meet Context-Free Grammar, 2 birds with 1 stone. This is not only a fascinating presentation, but despite the name, no birds are ever harmed in any of Dr. Gui's research. So I'll take the opportunity now to send it over to you, Hui.
Hi everyone, this is Hui. I am an assistant professor at the Computer Science Department of UMass. I'm going to present one of our recent work on accelerating RNN-based sequence modeling applications. RNN is short for recurrent neural network. It is one type of deep learning model that is very good at sequence modeling. For example, in the next word prediction task, you can use RNN to predict what is the next word you're going to type. After feeding the model with the inputs, we're going to discuss recurrent. The model may be able to predict neural as the next word. So when the next word, neural, is already typed in, it will feed into the model to predict the coming word as networks. Besides the network prediction, RNN is also applied to other data sequence-based applications. For example, it can handle function call trees to predict the next function call. This can help with the compiler optimization. It can also be applied to memory access sequence for data prefetch, some other sequence-related tasks, including system log analysis to predict the system failure, user activity analysis for personalized recommendations, and others. Although RNN is very effective in many sequence modeling tasks, the effective adoption of RNN faces two main challenges. First of all, we want the prediction to be as fast as possible. Take the next word prediction task as an example. Suppose you are using RNN for prediction or next word. If the next event is already arrived, even before your model can give you the prediction, then even though you have the prediction available, it won't bring any benefits. Besides the performance requirement, sometimes we also want to predict the next sequence of events instead of the next single event. For example, we can predict the next two words, neural networks, instead of just the neural. A larger prediction scope is more important if your application takes more time to handle the predicted results. For example, if you can predict the next several function calls, you can have more time to perform runtime code optimization to functions that run super slow. If you can predict the future events that are going to happen on a server based on the system logs, then you may have enough time to prevent a system failure. Our larger prediction scope can usually give you more time to plan for actions for other user activities and other data sequence. To address about two problems, our basic idea is to learn on compressed input sequence instead of the original sequence. A lot of data sequence contain repetitive patterns. For example, they are going to discuss may often appear together. We can reduce it to a single symbol. We can apply data compression to the input sequence to get its reduced form, the compressed inputs, and fit these inputs into the RNN model. Because the input data sequence to consume is much shorter, we are able to reduce the time to make our prediction. When we make a prediction, the predicted symbol can be a sequence of events instead of a single one. This can also help us increase the prediction scope. To see how we are going to apply this basic idea, let's first revisit the typical workflow of developing an RNN-based application. The workflow has two steps. One is offline RNN training, another one is online inference. So in the offline training, you will train an RNN model using your training inputs and your training targets collected offline. Then the model is deployed to handle streaming inputs and then make predictions. To apply compression to RNN applications, the first question to answer is how to compress the training inputs. And the second question is how to perform inference on streaming inputs. Next, I will talk about each of the challenge and its solution in detail. Let's look at the first challenge. So the tricky part about applying data compression to training data is to keep the statistical properties of the sequence such that the RNN can still learn patterns from the compressed sequence. Our solution is grammar-based compression and accuracy-conscious lowering. Grammar-based compression is related to context-free grammar. The CFG is a formal grammar that consists of production rules. The example here shows a production rule. It means the symbol 1 can replace the string ABC. The left-hand side is usually a single non-terminal symbol. The right-hand side is a sequence of terminals and non-terminals. Grammar-based compression aims to transform the input sequence into a context-free grammar. Let's look at an example. Given this sequence, we can apply a grammar-based compression algorithm called separator to produce a list of production rules. So the first rule shows the most compressed form of the input sequence. If you keep applying the other rules to extend the symbols in the first rule, you will get the original sequence. However, this most abstract form is not friendly to training at all, since it contains many symbols that appear only once or twice. To solve the problem, we apply accuracy conscious lowering. Its basic idea is to keep expanding the first rule until all the symbols in the sequence have a frequency that is larger than our threshold. We identify the threshold using binary search to meet the accuracy requirements set by the user, such as 0% or 1%. Now we have finished our first challenge. So after the first challenge is resolved, the online training will give us a well-trained RNN model that can compress the sequence as input. There is also a dictionary that encodes the meaning of each symbol used in the sequence. The next challenge is how to conduct online inference given that the input streaming inputs are not compressed at all. Our solution is tokenization with rollback. Essentially, the basic idea of tokenization is to replace the subsequence of events in the streaming inputs using symbols in the dictionary, while rollback tries to fix the problem caused by the nearsighted property of tokenization. It will roll back hidden states of RNN to undo the state changes when necessary. To understand the mechanism, we need to dive into the details of how an RNN makes a prediction. RNN is composed of recurrent units that continuously transforms the input hidden state to output hidden state. Prediction is made based on the hidden state. Next, I will explain how does tokenization with rollback work using an example. Let's see, at time t equals to 1, we have an input x. We use a tokenizer to compress the streaming inputs, and we get x as the output. After feed it into the RNN, we get a prediction that is 3, which means a sequence of A, B, C. And the hidden state is transformed from H0 to H1. At another time step, a new event is ejected. The tokenizer produces A as the output because the prediction at time step 1 already covers A, so A is not fed into the RNN for prediction. Then similar things happens at time step 3 when B is available. At time step 4, when C is the new event, the tokenizer realized that ABC should be replaced using 3, and thus report 3 as the symbol, as the output symbol. Also, because the previous prediction 3 is already exhausted, so we feed this new token, the 3, into the RNN for prediction, and it predicts a D. At time step 5, A is a new event because the previous prediction is wrong, so A is fed into RNN for a new prediction at this time. RNN predicts B. Then in the time step 6, you get B. Tokenizer produces B as well, and then this B symbol will be fed into the RNN and predicts the F. The scene becomes more interesting at time step 7 when C comes. Tokenizer again realized that ABC should be combined together into a symbol and thus outputs 3. However, 3 cannot be fed into the RNN model immediately because the model is not in the right state. The model state is already updated using the symbol A and B at prior steps. So we have to revoke these state changes. And we replace H6 with H4, that is a hidden state at time step 4, so that we can feed 3 into the model, and then the model can give us the right prediction. Until now, we have covered the 2 challenges and the solution to each of the challenge. Next, we will talk about the experiments. In our experiment, we evaluate the algorithm using 16 real-world data sequence, including program function calls, memory traces, and system logs. Each of the sequence contains 500,000 events, where the first 50% of the events are used for offline model training, and the rest is used for model inference. The RNN model we use is a typical model contains an embedding layer with 256 in dimension, a GRU layer with 1024 units, and a fully connected layer as an output layer. Our experiment answers 3 questions. First, can the new algorithm keep the accuracy satisfactory? Recall that we allow users to specify the accuracy drop they can tolerate. We experiment with 2 accuracy drop rate that is 0% and 1%. We compare our method, which gives you prediction based on compressed streaming inputs, and the baseline method that predicts the next event directly based on the streaming input. And obviously, the answer is yes. The method can keep your original accuracy. The second question is, what is the prediction speedup we can achieve? This table lists the speedup results for 4 of our 16 benchmarks. Overall, we can decrease the inference time by up to more than 1,000 times. The last question is about prediction scope. This table reports the average prediction length of 4 of our benchmarks. Overall, the prediction scope can cover an average of up to 7,000 future events in one single prediction. It is also worth mentioning that given the same prediction scope, the traditional approach will suffer from up to 54% accuracy drop. So in conclusion, this is the first work that integrates data compression into RNN to speed up RNN inference and enlarge the prediction scope. The proposed compressed learning approach implies a novel learning paradigm for sequence modeling. It addresses the tension between compression rate and inference accuracy through lowering and overcomes the myopic nature of online tokenizations through rollbacks. The compressed learning unlocks the potential of RNNs for many real-time applications. Thank you.
Okay, thank you, Hui, for an interesting talk. Are you able to turn your video on?
Yes.
Hi, Hui. Thanks for joining us. I guess I was watching the video and thinking, there's a number of different applications for recurrent neural networks that come to mind, and certainly with context, with things like translation software. Have you seen applications for recurrent neural networks in that realm? Because what I'm getting at is that context is so important in any type of language translation.
Okay, I think maybe for a lot of natural language processing researchers, they prefer transformer or attention-based model rather than LSTM, or like this type of traditional neural network models. I think the major reason we want to apply to system logs and the function calls is because there are still like some of the researchers tries to investigate whether this old type of sequence modeling can be applied to those system-oriented problems, and also because this kind of system-related context actually have such kind of data that has a repetitive pattern. It can easily imagine that a program can have a for loop such that it can have this repetitive pattern, or system logs because it install the same software again and again, so it has the same repetitive pattern. But these kind of things might not hold for like languages, because you probably won't speak the same thing over and over again. But there will definitely some other kind of situations that might also have data set or like have the time series that has this kind of pattern, such as like traffic signals. You probably also can observe similar patterns over and over, and then those are the data sets that will benefit from the proposed algorithm.
I see. Thank you for that explanation. We're going to keep to schedule right now, so we need to move right along to our next talk. And in that, for our final faculty talk today, Professor Yair Zick will discuss his work on creating explanations for the decisions that models make in high-stakes situations to help ensure fairness and transparency, while also protecting the trade-off of privacy. So here's Yair.
Hello everyone, my name is Yair Zick, and today I'd like to share with you my work on providing good model explanations. So, as you may be aware, we now live in a world where AI decision makers operate in a variety of high-stakes domains, such as healthcare, criminal recidivism, personalized recommendations, and finance. And this setup where we have complicated decision makers make such decisions in high stakes domains often necessitates the use of model explanations. And let me just give you a short intuitive example. So suppose that I walk into a bank, well, somebody does, that's not my profile, and they ask for a loan from the bank. And the bank, unbeknownst to them, uses some kind of a decision-making model, automatic decision-making model to decide whether they do or do not receive a loan. And their loan gets rejected, and they ask the bank, well, why? Why was it rejected? And now the bank has a bit of a problem, because if it were a human that made that decision, they can go back and ask that financial officer, well, why was this person rejected the loan? That person could tell them, okay, well, this applicant did not have a high enough income or some other reason. But if they go and they look back at the automated decision maker, they might not be able to give them an obvious answer. So just looking at the model and its internal decision-making process could be very complicated, because nowadays AI relies on very complicated architectures such as deep neural networks, random forests, and similar techniques. So how do we take this complex system that sometimes even updates its own parameters based on previously observed data? How do we take that system and translate what it does to a language that an end user might understand? So to do so, we have an extensive literature that has really developed in recent years that provides model explanations. And there's a very large variety of such measures, but we're going to focus today on a very specific one, which is called feature highlighting. Or in other words, how much influence do different features have on a classifier's decision? And this class contains several very prominent types of model explanations, including Shapley-based, optimization-based methods, and gradient-based methods. And what happens here? Well, we take every one of the user's attributes and we look at what the black box classifier or decision maker does with them, and to a limited degree, and we output for every feature a value. So small values just correspond intuitively to features that were not very instrumental in making the decision, whereas high values, for example here expenses and income, correspond to features that were important in making the decision. Some features can have negative values. So for example, here the amount of check in the checking account is negative because even though it is important for the decision, it's actually important for the other class. So in other words, people who get loans, usually people with this amount of money in the checking account, actually do receive loans. So how does one design model explanations? Well, in my group, we try to look at a variety of design criteria. So for example, fairness. So is this model explanation framework treating different groups of individuals in a fair manner? Privacy. So is this model explanation leaking information about other users when it provides an explanation to a client? And finally, explanation quality. So how good is this explanation? Is it any good? Does it satisfy certain optimality criteria? And indeed, for quality, one can take two approaches. One of them is optimization based. So, well, you take the point of interest, which is the point you're trying to explain, you take a certain region around it, and then you try to optimize and locally find some local approximation, the best one you can in that small neighborhood. And then you use that approximation to explain the decision. Another option is to optimize in terms of how much the model changes its predictions when certain points are added or omitted. And finally, another type of optimization is gradient-based optimization, which is also a very commonplace technique. The axiomatic approach, which I will try to convince you today that it makes sense, essentially says this. Before we decide on a formula for our model explanation, let us try to decide what properties we want the explanation to satisfy. And then we will try to narrow down what mathematical formulas satisfy all of the properties that we have laid out. And I think this approach makes sense because the model explanation literature has blown up so much in recent years. So let's say that now you have this data set and you want to explain the decision of the model for this specific point. You go and you do a short web search and you realize that there are several techniques in the literature. So you can think about like gradient-based techniques, Shapley-based techniques, and optimization-based techniques. So which one of them should you pick? And this decision could be very important because the type of explanation you provide may or may not fit the use case that you have in mind. So how do you do it? Well, we advocate for a normative approach, or rather a normative debate about the type of explanations you would want to provide. So you start by saying, okay, I want properties 1, 2, and 3, and based on these properties, I would look at what measures satisfy them, and these are the measures we should be using. And there are two big reasons that I think this is important. First of all, because while the mathematical formulas can be very complicated, the properties themselves are fairly easy to understand. And more than that, it allows us to have a debate that not just includes computer scientists in order to decide what model explanations we should be using. Right? So we debate the norms that are easy to understand rather than the formulas, which are often at times less so. So let me briefly tell you about two such axiomatizations that we have come up with in my group. The first one is a Shapley value-based approach to generating model explanations, which we call quantitative input influence, or QII for short. Now, if you don't know what the Shapley value is, that's fine. It's basically a way of dividing revenue in a collaborative game theoretic setting, which nicely lends itself to the model explanation framework. And what this formula says actually is not very important. What does matter for the purpose of this talk is what properties it uniquely satisfies. And these properties are symmetry, so two features that have the same effect on the model will have the same value, dummy, so if a feature has no effect on the model, it has no value, monotonicity, which says that if a feature has more effect on the model, it should have more value, and efficiency, which just says that if, so the sum of the model explanations values should be some natural constant. We designed a slightly more data-driven model explanation, which we called monotone influence measures in a paper with Jakub Slavinsky, Martin Strobel, and myself in AAAI 2019. And this model explanations uniquely satisfies, again, a set of different properties. So geometric invariance, so basically the explanations move as the data moves. Continuity, so small changes to the data result in small changes to the explanation. Monotonicity, very similar to the monotonicity notion I described before, and non-bias. So if we randomly label the data set, with different values, the expected value of our explanation should be 0. So we are not a priori setting more value to certain features. We also designed, axiomatically designed model explanations beyond just feature highlighting, but to feature set highlighting. So saying how important was a set of features rather than just one. And the motivation is fairly simple. So if we look at this data point, which is a movie review, which is labeled as a positive movie review. If you read it, then indeed it's positive. It isn't the greatest sci-fi flick I've ever seen, but it is not a bad movie. Okay, so not glowing, but still positive. And you look at these two features, words are features here, not and bad. Then if you look at them individually, they both have a negative connotation. But if you put them together, then they have a positive one. So it does make sense to talk about the synergy of features and measure its importance rather than the importance of just individual features. And we have done that. So here is a way of measuring the value of a set of features. So here phi of S, so S being a set of features, so how much value do we place on a single, on a set of features. And here, this way of measuring influence satisfies a set of desirable axioms. Again, very similar to what we said before. So symmetry and invariance under merging. So if you take two features and merge them, then the total influence should add up as well. Monotonicity, again, similar to the ones we described before. And limit condition, very similar to the summing to a natural constant that we described before. But not only is this axiomatic, it's also optimal. So these phi or S, these set-wise values correspond to the coefficients of an optimal solution to a natural optimization problem. So let me just briefly go over a fairness issue that we do discuss in our work. You can go ahead and read it. So fairness, what do I mean by that? Just that, well, when we offer model explanations to different people, then we need to be aware that our explanation quality may vary between groups. And then how do we handle that? Right, so if do we offer poorer explanations to different groups? Do we leak certain users' information more than we do other users' information? So all of these things you do need to consider and evaluate as you study this interesting topic. And privacy is another important design paradigm, as I've discussed. And we already have shown in prior work by Reza Shokri, Martin Strobel, and myself that model explanations can indeed leak information about user data if you're not careful. And they do so especially badly for minority groups, again, tying back to the fairness concern that I've mentioned before. And we also try to take steps to mitigate this issue by offering differentially private, so provably non-data leaking explanations. And what we did here, we took an optimization-based approach. We tried to minimize some natural loss function in a differentially private manner. And what we did is we basically showed how to optimize in a differentially private manner using differentially private gradient descent, and how to handle repeated queries to the data, because every single query leaks a little bit of information. We want to make sure that those don't add up in a bad way. So before I stop, let me just tell you what the main insight I have from all of this is that when you design model explanations, you face an inherent trade-off between these three desirable design criteria. So if you want good explanations, you will have to trade off fairness to groups and privacy. If you want privacy, you may suffer in terms of fairness and quality. You want fairness, then you may suffer in terms of privacy and quality. So when you design them, you got to be aware of these trade-offs and work to mitigate them as much as you can. So that's it for me today. Thank you very much for listening. And if you have any questions, please feel free to reach out. Thank you.
Okay, thank you, Yair, for that talk. Yair, if you can turn on your video, we have just a quick question for you before we end this faculty talk session. One question that came in over the chat asked, could you briefly describe how you would go about analyzing perhaps a series of model explanations to determine whether or not an algorithm or model was biased?
So we do, so you can look at individual explanations as a group and look, for example, if certain features are attributed any influence. So for example, if for a certain group, you see that a certain feature is constantly being used more than it is in other groups, that would be one indication. But we also offer other types. So for example, in the QII paper, the one with the Shapley value-based explanations, so I don't go into it with full detail, but we do offer methods for explicitly measuring these kinds of things. So like comparing the influence of certain features of the groups in a very organized sort of way.
Okay, great. Thank you for that explanation. And I'm also just want to comment that if there is any voting done during this symposium, I'm going to vote for you for the best Zoom background. Thank you, Yair.
It's from the CICS. It's not mine. But yeah, thank you.
Great. All right, so that wraps up our faculty research talk session. I invite everyone, if you optional, or you can take a break, or you can go to one of our breakouts, or our breakout session for the next 15 minutes, and perhaps talk to some of the faculty that you just heard about their research. So you can do that. Just take a look in the chat, and the instructions are in there for that link. And then you could use the your registration email that was sent to you in order to get back into the main session afterwards. So thank you very much. Thank you to all the faculty and all the work that they did for putting together the talks. And that concludes this part of the symposium.